Let's go. Okay. So last time we were almost done with chapter, well, halfway through chapter 28, right? We talked about resistors in series, right? And we got to, I think, power, the energy dissipated in the circuit. So we chose the simplest circuit possible, basically. You got the battery here. It has a certain voltage. There is a resistor. And then the circuit is complete. And the current will flow clockwise, right? The current will flow clockwise. And the question was, how much energy does it take to move a positive charge, a charge dq, from the minus terminal to the positive terminal? How much energy does it take? Well, it will take what? Q times delta times the voltage, right? So the amount of energy given by the battery to move a positive charge from here to here will be, we can call it du from the battery, and it is equal to dq times the voltage from the battery, right? And if you divide both sides by dt, dt will be the current. So if I divide both sides by dt, so this is the energy per second from the battery, so it's the power, E for power. So it's du dt. dq dt is the current, the power is P, so it's the current times the voltage from the battery, all right? Now where does the battery get this energy from? It's not out of nowhere, right? You use what kind of energy to convert it into electrical potential energy? Yeah, it's chemical energy, yeah. So there are, until the battery runs out of those chemical reactions. So yeah, it is chemical energy to increase the potential energy, right? Electrical potential energy. Now, the charge moves and then it follows the current. When it moves from here to here now, the potential energy of the charge decreases, right? It goes from high potential to low potential, so there is a loss of energy now. How much loss is there and where did it go? It goes to thermal energy, and the amount of loss is, again, it's dq times the voltage across the resistor. And the voltage across the resistor, in this case, the voltage across the resistor is the same as the voltage across the battery. So I'll just call it V for the voltage across the resistor, and that's du. And it's technically negative because it decreases, right? Because V here, the change in voltage is negative. But I just want the magnitude of the thermal energy, right? So this is negative, the thermal energy will be positive. So how much thermal energy is there? We'll divide both sides by dt again. And so you get the power, or the energy given off as thermal, as heat, would be dq dt, which is I times the voltage. So that's the power dissipated in the resistor. This is not the most common formula. Usually you see it this way. I'll give you two other forms. The current is V over R, right? The current in a resistor is the voltage across the resistor divided by R. Which law is that? Ohm's law, yeah. So it's V over R. So if I have here V over R times V, what do I get? V squared over R, yes, over R. And another one that you sometimes see, IE. V is IR, right? V is IR, right? V is IR, according to Ohm's law. So you have I times IR, so you get I squared R. I squared times R. We use this one a lot and this one also. I like this one. It seems more localized. It's the current through the resistor squared times the resistance of that resistor. This one that I use a lot. So toward the end, I might do an example on this one. All right. So I want to get through the The next unit is the, we talked about resistors in series, and we said this, resistors in series. It looks like this. So R1, R2, and R3, and so on. If you were to replace them by just one resistor, that would be the equivalent, R equivalent. And R equivalent was what?
R1 plus R2.
The sum, yeah, R1 plus R2 plus R3, and so on. Oh, good. Did we, yeah.
To go back really quick.
Yeah.
For power, you said DE thermal.
Yes.
Is that the same thing as power?
No, DE dt.
Yeah, DE dt.
Yeah. So the energy per unit of time?
Oh, so, because you said the E was thermal energy, so as you divided that by dt, right? So the power you said, is that a power for the thermal energy?
So, okay, so this is, okay, so we have two things. So it's losing electrical potential energy at this rate. So it's losing electrical potential energy. So if you're talking about electrical potential energy, you'll have a minus sign. That's how quickly it's losing it. And it loses it to thermal energy, so thermal energy is being given off at this rate. So they're negatives with one another. So if you divide by delta T, so this is how much thermal energy you're giving off per second. And that's equal to how much electrical energy you're losing per second. Yeah. So, oh, my question was, we did this one, I do remember it vividly. I don't remember though if we did parallel or not.
We did.
We did.
We did.
We did.
We did not.
We did.
We did, okay, that's great. So here is the parallel connection. So here is the parallel. Something like this, right? R1, R2, and R3. And if you were to change all of these resistors and replace them by one resistor, what would it be? It's called R equivalent, right? And R equivalent in parallel is that 1 over R equivalent, 1 over R1, plus 1 over R2, plus 1 over R3, right? Okay, so that is for resistors in parallel. So let's do a quick example. Although in the worksheet has plenty, but let us do a quick example for a combination of series and parallel before I go on to charging and discharging a capacitor. And that will bring us to the end of this chapter. Actually, I need to talk also about real batteries, how they behave. So here is a combination. So this is an example. So you have a resistor, a resistor, a resistor, and then a resistor, and then a resistor here. And they're connected probably to a battery or something. But we want to replace all these by just one resistor, they're equivalent. So this one here is 9 ohms. This one is 45 ohms. 9 ohms, 45 ohms, 25 ohms. And I copied this one from the book, but I forgot to copy this number. So let's make it up. Let's make it 5 ohms. Okay. So which means I will not have the answer, so you have to help me. Okay. Yeah, I forget to write that. Okay. So we have this. So what should we start with first?
Two parallels.
These two are in parallel. Okay, so they're in parallel, so we need to do 1 over, right? So the way you go about this, redraw the circuit, so you will have your 5 ohms that we just made up right now. And then these two capacitors, these two resistors, I'm sorry, they're going to be replaced by just one resistor. And we need to figure out the resistance of that resistor. This is the 20.
I got 3.
5. And so, yeah, we want to find this one. So apparently it's 3.
I
Okay.
got it, yeah.
So we will, let me just write the details and then, yeah. Thank you. So again, these will become this. And so the way you would find the equivalent, you would do what? 1 over 9, right? Plus 1 over 45, right? So this is 5 over 45, isn't it? And so it becomes 6 over 45.
Mm-hmm.
Then reciprocate that.
And then reciprocate that, so you got 45 over 6, which is 15 over 2, which is 4.5? No, 7.5.
Yeah.
Yeah.
7.5.
Is it?
Wait,
It's
wait.
7.
Oh, it's
yeah,
45. Is
7.
it 4.5 or 45?
It's 45.
I thought it's 45.
Oh, I'm sorry, that's, yeah, no.
Oh, okay.
7.5.
So this one would be,
7.5.
so when you reciprocate, you have to put to the power minus 1, so 7.5? Okay, 7.5 ohms. So, is everybody clear on this? If you're not, you should plug it into your calculator and do it for real. So put 1 over 9 plus 1 over 45, and then do 1 over that result, and you should get 7.5 ohms. So this becomes 7.5 ohms. Okay. This is ohms. Next, what's the next thing that we need to do?
Series.
Add them together.
These two are in
7.5
series.
plus
Good. So these two are in series. So my circuit now becomes this.
Is 12.
I have my 25 here, and I have these two. They're in series, so that's the easier one, right?
Mhm.
You don't have to do reciprocals. You just add them. So 12 and a half, right? So 12.5. Ohms. Ohms.
Yes, we're.
So, okay. Finally, these two are in what combination?
Parallel.
Parallel. So
9.5.
it becomes this. These two, this whole combination gets replaced by that one resistor.
Mm.
Well, they're in parallel, so you do 1 over 12 and a half plus 1 over 25, and then 1 over that. So you do 1 over 12 and a half plus 1 over 25. So this is 2 over 25, so it's 3 over 25, so it becomes 25 over 3,
I got 8.33.
8.3. Thank you. So that's the answer. Again, in the worksheet, I have many more than this. That we've been going over. All right. Next, I want to just quickly talk about real batteries. And then charging, discharging capacitors, and that should put an end to this chapter. 28. So I want to reserve this for charging, discharging capacitors. I would like to erase this if possible. So I wanna, if anybody wants it, I will give you one minute to do that before I erase. So real batteries. So for ideal batteries, we said, what's their resistance?
0.
Yeah, they have 0 resistance. And so for an ideal battery, it looks like this, right? It's an ideal battery. So in principle, if I connect an ideal battery to itself, and the wire is ideal also, what would the current be?
Infinity.
It would be an infinite current, so the battery will just die immediately because it has a certain amount of chemical reactions. Infinite current, so battery is dead immediately. In practice, it's not this way. So the current, first of all, is not going to be infinite. And so, in practice, so this is ideal. In practice, it's not ideal. It will have a certain amount of resistance. So even if you connect the battery to itself, the current is not going to be infinite. The current will be, so let's do some practice. So let's say the EMF of the battery is this. What would the current be? What would you do to find the current?
I equals
V equals
E over R.
Okay, yeah. You can use the loop rule, or you can just say, I mean, you just have one resistor here. In fact, let me use the loop rule. So the loop rule says, when I go around the loop, I get 0, right? So if I go from here to here,
E.
an increase of E. When I go from here to here, the current is in this direction. So moving in the direction of the current, I decrease by IR, right? And that's it. I'm back. So I get 0, and so the current therefore will be the voltage over the resistance, right? So it's not going to be infinite. It's going to be large, but not infinite, because R is not 0. All right, so with that said, let me go to charging, discharging. I might come back to something like this in a moment. But let me go to charging and discharging of capacitors. So first, to use a capacitor, you have to charge it before you discharge it. The book discusses discharging before charging. I will use the charging first. I will discuss the charging and then discharging. So we will charge our capacitor and then we will discharge it. Charging. So a capacitor charging looks like so. You have a battery, and it has a certain voltage. You will have a resistor, R, and then you will have a capacitor now, resistor with a capacitor. And the circuit is open, so the capacitor is completely discharged at the beginning. It has nothing in it. It has no charge in it or on it. So what's the initial charge on the capacitor therefore?
0.
0. What's the initial potential difference between the capacitor plates?
0.
0. So there is nothing on the capacitor. So now I close the circuit and let's see what we get. Alright, so I close the circuit. Let's do the loop rule. So the capacitor will start, the current will start to flow. As the current flows, plus charges will stick here, and minus charges will be here, right? Yeah, because pluses will be leaving this place and being piled up in this one. So you have pluses here and minuses there. And so let's go around the loop and see what we get. So just to emphasize, here is plus, and here is minus. For the battery, the pluses are here, this is the minus, right? All right, let's apply the loop rule and see what we get. You go from here to here. What happens? What's the change in potential?
Negative. Oh,
From-
digital positive, sorry.
Plus, yeah, you
Yeah.
jump by 8. The current is going this way, right? That's the current. Now, you go from here to here. What happens?
Minus three.
Decrease or increase?
Decrease.
Minus 3.
Decrease by
IR.
an IR, yes. Is everybody clear on this one? That you decrease by an IR, right? The voltage drop across the resistor, the voltage drops because you go from, because current flows from high potential to lower potential. So you decrease. Next, when you go from the positive end of the capacitor to the other end, what's the change in voltage? Is it plus or minus? It is
It's a
minus
minus.
because the positive end is at a higher potential than the negative end. So it's minus the voltage across the capacitor, right? VC, the voltage across the capacitor. And I've completed the loop, so I set it equal to what?
Zero.
Zero. Good. Alright, so let's see. So I have here, the EMF of the battery minus the current. How is the current related to the charge? Slowly.
Q equals I over
I equals
T.
to what?
Okay.
dq dt. Yes, it is, remember current is dq dt.
Oh, yeah.
And the current has the right direction, so it is just dq dt. So the current is dq dt. dq dt times R minus the voltage across the capacitor. Remember how it's related to the capacitance
equals
of the
CV.
charge?
Over R?
V is Q over C,
Oh,
Q equals CV.
right? Yeah, Q equal to CV. And so Q over C is the voltage of the across the capacitor. That's Q over C equals to 0. Are we okay so far? If you see a mistake, tell me. Here it is. Now, let me, let's move this to the other side and see what we have. So we have this R times dq dt is equal to EMF minus Q over C, right? Divide both sides by R. Divide both sides by R. I'm taking my time to solve this equation. We will solve it's called the differential equation, right? You have the derivative of something equal to on one side and something on the other. So you got dq dt is equal to EMF over R, EMF over R, and then 1 over RC times Q, right? The R came from divided by R, so it becomes RC. Right. To solve this, there are a couple ways, but I think the easiest way is to change variables. I would just change variables instead of directly integrating. So here's what I mean. Ready? For the, okay. So I'm going to make a new variable called capital X. So let x equal to E over R minus Q over R C. That's X. Therefore, dx dt. Therefore, dx dt will be what? What's the derivative? Is the battery EMF changing?
No.
No. The resistance of the resistor, is that changing?
No.
No, it's constant. So all these are constants, so their derivative is 0. You have negative. Again, this is a constant, so 1 over RC. And then the derivative of Q with respect to time is dq dt, right? dq dt. So solve for dq dt in terms of this x. So you'll have dq dt will equal to minus RC times dx dt, isn't it? Alright, so now we're ready. So dq dt is what? I'm referring to this equation now. dq dt is
Current.
minus RC dx dt, right? dq dt is minus RC dx dt equals, and this EMF over R minus 1 over RCQ is what?
dq dt.
That is just X, yeah, that is X. It's X, yeah. Right, this stuff is what we call X. We will go back to the original variables in a second, but for now, that's what I have. So dx dt is equal to minus 1 over RC times X. Now you can integrate this, or you can just think about something, you take its derivative, you get back the same thing, multiplied by a constant. What is that thing?
It's
Huh?
e to the x.
e to the something, yes. It is the exponential function, yes. So yes, in fact, x of t will be some constant in front, which I'm going to call a for now. And then e to the minus t over rc, that's the solution. Why? Well, take its derivative and you will see. What's the derivative of this? It would be the same thing multiplied by negative 1 over rc, right? Because the chain rule will give you negative 1 over rc. So negative 1 over rc comes from the chain rule. So this is the solution. Now I'm going back now to my original variables. So I got x, but now I'll just go back to my original variables. So I'm going to use this equation. So x is this, EMF over R minus Q over RC equals A e to the minus T over RC. To find A, this constant A, we have to find it, figure out what it is. What is Q at T equal to 0? What's the charge on the capacitor? T equal to 0.
Zero?
It's 0. Yeah, right? The capacitor started not charged. So at T equal to 0, the capacitor was not charged, so Q was equal to 0. So let's see what we get. Let's plug in 0 for T and see what we get. So I got, on the left side, I would have Q is 0, so this is 0. I would have EMF over R equals, when I plug in 0 for T, I get what? E to the 0, right?
1.
And e to the 0 is 1, so A. I get A. So this A is just the EMF of the battery over R. That is A. So let's go back to our equation. EMF over R minus Q over RC is equal to EMF over R e to the minus T over RC, right? And multiply everything by R and then solve for Q. So Q would be what? You can move this to this side and this one to the other side. Q would be EMF times C times 1 minus e to the minus T over RC. That's the answer. This is some algebra. Going from here. Okay. Yeah.
At t equals 0, isn't c also equal to 0?
No. The capacitance is geometric. Epsilon naught A over the area. I'm sorry, epsilon naught, the area of the plates divided by the distance between the plates.
Okay.
Yeah. So capacitance is actually not 0. It's some number. Yeah. So that is the charge on the capacitor. If you were to graph charge versus time, well, the capacitor would be charging, right? It was 0 at the beginning. So again, if you put 0 for T, what do you get? E to the 0 is 1, right? 1 minus 1 is 0. So Q at T equal to 0 is 0. So if you plot it, here is time, here is Q. It starts at 0. As T goes to infinity, what do you get? What is e to the minus infinity? 0. So you have 1 minus 0 is 1. So it approaches this value, this horizontal asymptote, right? So it will look like this. It will approach this value. The capacitor will charge. So this is Q. This value here is Q max. Now, if I ask you what's the voltage of the capacitor as a function of time, what would you say?
Q divided by
Q divided by C. Here is Q. Divide that by C. So the voltage across the capacitor, VC, will be Q over C. So divide this expression by C. It would be just the EMF of the battery times 1 minus e to the minus P over RC, right? Yeah. Next, if I ask you, what is the current? How would you find the current?
V equals IR.
It's equal to IR.
V equal to IR, but what's the voltage across the capacitor, the resistor though?
Oh, okay,
I.
Yeah. There's an easier way. What's the relationship between current and charge?
I equals Q over T.
dq over dt,
dt.
dq dt. So you have Q as a function of time, take its derivative. So current dq dt. Well, let's see what you get. When you multiply, well, this is a constant in front, so take the derivative of what's inside. Derivative of 1 with respect to t is 0. Derivative of this with respect to t will give you negative 1 over RC out. But there is a minus here, so it just becomes 1 over RC out, right? But there is EMF C, so you just have EMF over R, e to the minus P over RC. That's the current as a function of time. So when you, let's plot the current now versus time. Will the current increase as a function of time or will it decrease?
Decrease?
It would decrease. See, when you close this, as the capacitor starts to charge, it's harder and harder to put charges on it. You can only put so much charge on it. Until the voltage across the capacitor is equal to the voltage of the battery, then that's it, no more current flows. Right? So let's plot this. The current as a function of time. Here is time, here is the current. At t equal to 0, what's the current?
0? Oh, wait.
The charge is 0, but not the current. See, when you close the circuit, it's like you just have a resistor. The capacitor didn't even come into play yet. So it's just E over R. The EMF of the battery, the voltage across the divided by the resistance. So that makes sense. At t equal to 0, e to the 0 is 1, so you just get E over R, the EMF over R. But as t goes to infinity, e to the negative something approaches 0. So it goes like this. Current is decrease. It goes to 0. Alright, so there is that. I have one more job to do, which is discharging this capacitor. Okay. And so this formula here is for charging. I mean, it really is just one formula, it's just this one. This one I got just from Q over C. And this one, by the definition of current, it's dq dt. So it's not like 3 different formulas. And I'm going to go to now to discharge. Now, to discharge a capacitor, it means what? The capacitor is initially charged or not charged? Initially charged, so it has some Q on it, right? It has some charge on it. Because if it's discharged, then you can't discharge. It's just discharged. There's nothing. So initially, the capacitor has charge Q0 on it. Right. Capacitor has charge Q0 on it. So here is the capacitor. Here is the resistor. Here are the plus charges. Here are the minus charges. My circuit is still open. Right? My circuit is still open. And my capacitor is charged. So now I want to discharge. So I need to close the circuit. Right? I'm going to close my circuit to discharge this capacitor. So the circuit is now closed. What happens to the plus charges? It will start to flow, right? They want to meet those minus charges. So the current will start to flow. So this is the direction of the current, right? Is it for sure the direction, or it could be the other way?
For sure.
It's for sure. Yeah, okay, good. So that is the direction of the current. I'm saying this because I will need to refer to that in a second. So that is the direction of the current. So let us now see, as a function of time, what happens. Well, I'm going to apply the loop rule again. We go from here to here. What's the change in voltage?
Negative.
Uh,
DC.
from
Oh,
here-
positive, sorry.
It's positive, right? It's positive the voltage across the resistor, right? Right? It's the voltage across the across the capacitor. Sorry, this is the voltage of the capacitor. And now when we go from here to here, do we increase or decrease?
Decrease.
We're decreasing because we're following the current. The current flows from high to low. So minus IR, right? And we're back to here, so this says equals to 0. Now, the voltage across the capacitor will be the charge on the capacitor divided by the capacitance of that capacitor, right? So the voltage of the capacitor would be just Q on the capacitor divided by the capacitance. Move this to the other side so you get IR. Now, how is I related to Q?
That's delta Q over delta T.
In terms of derivatives, it's dq dt, right? I claim though, in this case, it's negative dq dt. Why?
Because you're discharging.
You're discharging, so dq dt is a negative number. So negative of dq dt would be a positive number. And the current has to be positive because that is the actual direction of the current. Okay? Yeah. So the current would be, in this case, minus dq dt. So, so you got, well, let's, Q over C equals to minus dq dt times R. Divide, multiply both sides by R. No, divide both sides by R at the minus sign. So you would have dq dt would equal to minus 1 over RC Q. I don't need to deal with that change of variable x because this is already convenient. So derivative of something equals to itself times a constant. So the function has to be what? E to the something, yes. So Q of t, Q is a function of time, therefore, would be some number, some A, some constant A, which I need to figure in a moment, e to the minus t over RC. So at t equal to 0, what was the charge?
0.
Q0. So at t equal to 0, I must have Q0. Well, e to the 0 is 1, so this A has to be Q0. So since Q at 0 is equal to Q0, and so A has to equal to Q0. So therefore,